What is time? We feel it constantly. The urgency of a deadline, the nostalgia of an old photo, the slow creep of a sunrise. It seems to be the most universal and reliable river, carrying us all from the past through the present and into the future. But what if I told you this river is an illusion? A powerful one, yes, but one that, at the most fundamental level of physics, might not even exist. Today, we're going to explore one of the greatest unsolved mysteries in science, the problem of time. Why do our two most powerful theories of reality, Einstein's general relativity and quantum mechanics, profoundly disagree on what time really is? Strap in, because we're about to see reality in a whole new light. To understand the problem, we need to meet the two titans of modern physics. First, Einstein's general relativity. Here, time is not a solitary river. Einstein wove time and the three dimensions of space into a single, four-dimensional fabric, space-time. In this view, the past, present and future all exist equally. The universe is like a giant, unchanging block. A block universe. Time is just a coordinate in this block, and its flow is relative. Motion and gravity can stretch and warp it. A clock on a satellite ticks measurably faster than one on Earth. Time is malleable. Now, let's look at the other side. Quantum mechanics. This is the rule set for the tiny world of atoms and particles. And here, time is rigid and absolute. It's the universal external clock that Newton imagined, ticking away in the background against which quantum events unfold. The equations of quantum mechanics need this fixed time to describe how a particle state changes from one moment to the next. So, on one hand, we have a flexible geometric time that can be bent. On the other, a rigid background time that cannot. They are fundamentally irreconcilably different. This clash isn't just academic. It becomes a full-blown crisis when physicists try to combine these theories into a single theory of quantum gravity, a framework to describe the earliest moments of the Big Bang or the core of a black hole. The most dramatic manifestation of this is called the frozen formalism, or the problem of time. When you apply the rules of quantum mechanics to the entire cosmos described by general relativity, something shocking happens. The time variable cancels out. The fundamental equation that describes the universe, the Wheeler-DeWitt equation, suggests a static, unchanging reality. There is no then or now. The entire universe just is. Think about that. The most fundamental law of physics seems to have no place for time at all. So, if the universe is timeless, why do we, living inside it, experience such a powerful and relentless flow? If time isn't fundamental, where does it come from? Physicists have some mind-bending proposals. One leading idea is that time is an emergent phenomenon. It arises from more basic ingredients, much like temperature emerges from the jiggling of atoms. A fascinating version of this is the Page-Wouters mechanism. They proposed that for an observer inside the universe, time emerges through quantum entanglement. Imagine two parts of the universe becoming entangled, like a clock and the rest of the cosmos. For an internal observer, comparing the clock to events, time appears to flow. But for a hypothetical godlike observer outside the universe, everything is stationary. In 2013, a photon-based experiment provided the first experimental support for this idea. Another proposal is the thermal time hypothesis. Carlo Rovelli and others suggest that what we perceive as time is fundamentally linked to the increase of disorder or entropy. The arrow of time, why we remember the past but not the future, may simply be the universe's journey from order to disorder. There are other ideas too. The evolving block universe, where the future is not yet real, or the possibility that time is discrete, not continuous, at the Planck scale. The debate is wide open. So, where does this leave us? Physics cannot yet agree on what time is, because our deepest theories present us with a paradox. Is it a fundamental river, or a magnificent illusion born from our limited internal perspective? Is it a coordinate on a block, a consequence of entanglement, or a story told by increasing entropy? The mystery of time forces us to confront the nature of reality itself. It reminds us that our experience is just a slice of a much stranger, more wonderful cosmos. The next time you glance at a clock, remember, you're not just checking the hour. You're witnessing one of the deepest and most active frontiers of human knowledge. The quest to understand time is far from over. It remains an open book.